Thanks everybody for joining us for our Research and Discovery Grand Rounds. We're going to get started in just a couple of minutes. While we're waiting to get started, I just want to remind folks that if you aren't a member of Frontier CTSI, we want you to be a member so that you can be kept up to date on funding opportunities and important events like the one we're having today. So just as it says on the screen, just go to frontierctsi.org and it takes you about 30 seconds to become a member and be part of the club. I think we've got, what, 750 members and growing at the present time, so you don't want to be left out. We want to make sure that you're also aware of upcoming events like the Research and Discovery Grounds next May, where we'll get to hear Dr. John Tifo talk about his Center for Metabolism and Obesity Research. It's one of the 3 COBRIs that we have on campus. He'll talk a little bit about the COBRI mechanism and the structure and get into some of the details about some of the exciting work going on in the Casey Moore COBRI. So that's a presentation that you'll want to hear about. They've engaged so many people in that effort. It's a true exemplar of really burgeoning team science. So hope you can join us for that. Okay. Well, Dr. Collins, I'll let you, let me go ahead and do some introductions. So we have 2 speakers today, and I'm really excited about this presentation. I got to hear some of their work at the D&I conference in Washington, D.C. this last December, and I was so excited about the work that they're doing and the potential implications for their work for a lot of the intervention work that we do here. So I'd like to introduce Dr. Linda Collins, who's a professor of global public health in the Department of Social and Behavioral Sciences at NYU. She earned her PhD in quantitative psychology at the University of Southern California. She's the director of the Center for Advancement and Dissemination of Intervention Optimization, or CADIO for short. So you can just search for CADIO NYU and you'll find out more. We'll hear a little bit more about CADIO at the end of the talk today. She is currently collaborating on research applying most designs in the areas of smoking cessation, prevention of excessive drinking, and risky sex in college students, and HIV services with funding from the NIH and the National Science Foundation. And joining her today is Dr. Jillian Strayhorn, who's an assistant professor in the same department of social and behavioral sciences in the Global Public Health School. She's the associate director for CADIO. She earned her PhD in Human Development and Family Studies at Penn State. She is a quantitative methodologist and a decision scientist whose research focuses on complex multi-criteria decision-making that goes into optimizing multi-component interventions to achieve optimal public health impact. And so without any further ado, Dr. Collins, I think I'll turn it over to you to get us started today.
Okay.
Oh, actually, just one thing. I think folks may be able to put in questions, but feel free to use the chat. We'll be monitoring the chat, and if it's a critical thing, we'll interrupt. We have the ability to interrupt, but otherwise, make sure you get your questions in the chat.
Okay. Well, it's really great to be here today, and thank you for the nice invitation. I'm going to start by introducing intervention optimization by the multi-phase optimization strategy, MOST, and talk about some implications for implementation science. And then my colleague Jillian Strayhorn will take over and talk about decision-making and some other aspects of this interesting topic. So let's talk for a moment about the mission of implementation science, which is to ensure, I would say, that evidence-based interventions have a strong, positive public health impact. In other words, we need to ensure that evidence-based interventions are actually used and not put on a shelf because they're too expensive or too time-consuming or too complicated, that they're used with fidelity, and that they are effective across a variety of populations and settings. Now, there's an idea that's been implicit in much implementation science to date, and it's so embedded in implementation science that it's something that is often not questioned or talked about. And that is the idea that an intervention is developed, and very often in an academic setting, and then it's handed off to implementation science for further study about its implementation. Now, the intervention may be easy to implement, which is great. It may be difficult to implement, which is challenging, or it may be impossible to implement, which means it's going to be put on the shelf that I talked about a moment ago. So if the intervention is difficult or impossible to implement, that is, if it's not practical, what then? So while you're thinking about that, I want to make 2 points that I'll go over today. One is that it's possible to engineer evidence-based interventions to be both effective and practical. And secondly, that it's possible to engineer implementation strategies themselves to be both effective and practical. And I'll talk about that a little more at the end of my portion of this presentation today. So here's a schematic of the classical treatment package approach. There's a number of intervention components. I have 5 here, but of course, it could be any number of intervention components. And they are identified by the investigator, usually pilot tested, and then assembled into an intervention package. And that package is then evaluated, usually by means of a classical evaluation, RCT. We're all, I think, familiar with that experimental design. It's a pretty straightforward experimental design where participants are randomly assigned to participate in the intervention or a suitable control, and then the means of those 2 experimental conditions are directly compared, and you want to observe that the mean of the intervention is significantly better than that of the control. And the vast majority of intervention research uses this experimental design almost exclusively. And right there, when you start to think about it, all of us as scientists, I think, were taught that first, that the scientific question should drive the choice of experimental design. And second, that no one single experimental design is going to address every scientific question. And yet, we've really been giving the classical evaluation RCT a workout for a number of years in intervention science. So I'd like to introduce an alternative framework today, an alternative to the classical approach, which is the multi-phase optimization strategy, which we will abbreviate as MOST. MOST is an integration of ideas from a number of different sources. Of course, behavioral science is one of these sources with evidence-based strategies. The principle of optimization, which we make extensive use of, comes from industrial engineering, industrial and control engineering. Health economics has influenced these ideas, principles about management of resources, which are always finite. Decision science, methods for making difficult trade-offs strategically. Jillian has kind of specialized in that. And of course, implementation science, methods for achieving implementable interventions. So what is optimization? We define optimization as the process of achieving intervention ease. And let me explain what I mean by that. Intervention ease is a strategic balance of effectiveness, affordability, scalability, and efficiency. And the idea here is that you might be able to identify the most effective intervention. Perhaps that's sort of the Cadillac version of the intervention, but although it's very effective, it might be ultimately not implementable. It might be too expensive. It might be too complicated. And so a strategic balance of effectiveness against other considerations like affordability, scalability, and efficiency will end up with an intervention that has a better public health impact. And of course, I don't have to tell you that the public health impact of an intervention is exactly zero if the intervention is never implemented. So we talk a lot about this strategic balance of effectiveness against affordability, scalability, and efficiency to achieve intervention ease. And you might be thinking, well, that's great. It's a great idea, but how could you do that? And we would like to suggest that optimization by means of the multi-phase optimization strategy is the way to achieve intervention ease. I'd like to make 2 points about optimization. The first point I want to make is that optimization is not about finding the absolute best, but instead the best you can actually use. And the second point is that there may not be one single optimal intervention. What is optimal may vary across settings. It may vary across time. It may vary across resources. If you have different levels of willingness to pay, the optimal intervention will be different potentially. This is a schematic of the multi-phase optimization strategy, or MOST. So let's walk through this. There's a preparation phase, an optimization phase, and an evaluation phase. In the preparation phase, the investigator lays the groundwork for optimization. Now, a lot of what's done in the preparation phase you're familiar with already. You derive or possibly revise an existing conceptual model. Based on this conceptual model, you identify a set of candidate intervention components. And notice that we use the word candidate. In the classical approach, you identify a set of components and it's a foregone conclusion that they're all going to make it into the intervention package. But in MOST, they're candidate components because you're going to test their effectiveness in an optimization RCT in the next phase. So some of them will make it into the intervention, others may not. Any pilot work is conducted in the preparation phase. And here you identify the optimization objective. The optimization objective is an operational definition of what your objective is in optimizing an intervention. So for example, you might know that the most you can pay to implement an intervention is $500 a person. And so then your optimization objective might be to identify the set of components that will give you the most effective intervention for $500 a person. That's just one example. There's many, many other possible optimization objectives. Next, we move to the optimization phase of MOST, and here is where the investigator builds the optimized intervention. There are, in the optimization phase, you conduct an optimization RCT, which is different from an evaluation RCT. And I've listed here some possible experimental designs you could use for an optimization RCT, a factorial experiment, a fractional factorial experiment, and let me say parenthetically, we don't have much time today, but I will assert and send you to some literature if you're interested, that factorial experiments are much more efficient than you may be thinking. There's a pervasive myth in intervention science that factorial experiments require huge numbers of participants to power, and the opposite is actually true. It's kind of interesting. They actually are more efficient in terms of use of experimental subjects than other comparable experimental designs. The sequential multiple assignment randomized trial, which I heard just before we got on this session that some of you are interested in, that is one optimization trial design. It's a design that is used in optimization of adaptive interventions. The micro-randomized trial is also used in optimization of adaptive interventions. So once you've conducted the optimization RCT and you have the results, you then use the results also alongside whatever the optimization objective is that you identified previously, and other information such as information about cost or whatever else is going to go into the mix, and you identify the intervention that meets the optimization objective. And then if you wish, you can proceed to the evaluation phase and confirm the effectiveness of the optimized intervention in an evaluation RCT. So I just want to go back for a second to the optimization objective. This is really critical. People sometimes ask me, do you have to identify the optimization objective in the preparation phase? No, you don't have to identify it there, but it's a good idea to do so because you want to make sure that when you're conducting the optimization RCT, that you collect the right kind of data. For example, it would be a shame not to collect data on cost and then realize after you conducted the optimization RCT that you had hoped to use cost as a consideration in optimization. So to go on about the optimization objective, suppose to be implementable, an evidence-based intervention must cost less than $300 a person to implement. You can optimize by selecting the components that deliver the best expected outcome for a cost of less than $300. But also you can use time. So maybe it's been determined that an evidence-based intervention must take less than 30 minutes of staff time to implement. For example, it could be an intervention that's taking place in an emergency department setting and time is at a premium. In a case like that, you could optimize by selecting components that deliver the best expected outcome without exceeding 30 minutes of staff time for implementation. Okay, and I just want to remind you that the classical evaluation RCT is a part of most. We haven't thrown the classical evaluation RCT out, and those of us working in this area are definitely not anti-RCT. We are just pro using the experimental design that addresses the research questions at hand. So there are two ways that we see that most can contribute to implementation science. Most enables development of evidence-based interventions that are optimized to balance effectiveness, affordability, scalability, and efficiency. And it also enables development of intervention strategies that are optimized to balance effectiveness, affordability, scalability, and efficiency. I have heard through the grapevine that someone in the implementation science field has been saying that if most were to catch on, that there would be no more need for implementation science. And I just want to go on record as saying that I completely disagree with that. I actually think that implementation science can do a lot more if it starts with evidence-based interventions that, at least in theory, are practical to implement. So let's first talk about this first point. I'm going to give you a really quick example. This is a study that took place in the obesity area. It was published in the journal Obesity, and it's called Opt-in. And Bonnie Spring at Northwestern and I were MPIs on this project. The objective was to develop an entirely remotely delivered, technology-supported weight loss package to maximize the amount of weight loss that could be attained for an implementation cost of less than or equal to $500 a person. These were the components that were being examined. There also was a core component that we did not experiment on, but everyone received. So there were these 5 components: coaching calls, 10 to 15-minute calls from a health coach. People got either 24 or 12 in the experiment. Text messages, people either received them or didn't. Meal replacement recommendations. A report about weight loss progress sent to the primary care physician, and buddy training. Each of these was yes or no. And about buddy training, everyone who was in the experiment had to be able to identify a buddy. So everybody had a buddy. What was varied was whether the buddy received special training about being a good weight loss buddy. So let's quickly compare 3 alternative approaches. So you've got these 5 components on the table. If you've been trained primarily in the RCT, you might think, okay, I'm going to do 5 individual little RCT type experiments. So vary each component at a time, treatment control 5 times. If you do that, that would require about 2,600 participants to power. So you actually could save a little bit by doing what's sometimes called a comparative treatment experiment. This goes by a lot of different names. But the idea here is that there would be 6 experimental conditions, 1 shared control group, and then an experimental condition corresponding to each component, where that component is set to on and all of the other components are set to off or low. So that is some savings, would require only about 1,500 participants. The third alternative is a factorial experiment. This would be a 2 by 2 by 2 by 2 by 2, or we start using factorial notation when there's a lot of factors, a 2 to the 5th factorial experiment, that would require only a little over 500 participants. And that gets back to what I said before. The factorial experiment is a lot more efficient than you might be thinking. Of course, there's all those experimental conditions that need to be implemented. That's not necessarily a small thing. But I want to point out, look at that last column on the far right. If you take option A or option B, you cannot look at interactions between components, and with a factorial experiment, you can, and they can be interesting. So if you don't believe me, and I can send my slides if you're interested, there are a number of articles that explain exactly why the factorial experiment is so efficient in terms of use of experimental participants. So once you've collected an optimization randomized controlled trial, like the one I just described, you analyze the data, obtain estimates of the effects of each of the components, and you use that information to select components. You can discard components that do not perform adequately, and then you can select the components that will make up the optimized intervention, again, taking cost broadly defined into account. So here's what we learned. The optimized intervention turned out to be PCP report plus buddy training plus 12 coaching calls. That's the lower level of coaching calls. No text messages, no meal replacement recommendations, which it turned out everybody really hated. And this best met the optimization objective at a cost of $427 per person. But the least expensive intervention, which was 12 coaching calls only, cost $324, and this was the next best. And that's the kind of information that an optimization trial will give you that's really hard to get with the classical approach. So this one met the optimization objective, but this one was the second best and cheapest. Returning to optimization based on the results of an optimization trial, I kind of glossed over that, but the selection of components can be a complex decision-making problem, and that's particularly true if you have more than one outcome that you plan to make the decision on. We've developed an approach called Decision Analysis for Intervention Value Efficiency, abbreviated as DAVE. That's not what we used in the opt-in study because it hadn't been developed yet, and Jillian is going to be talking more about DAVE shortly. So let's talk about the second way that most can contribute to implementation science. So here's one way to hypothetically approach the optimization of the delivery of the opt-in intervention. So we've optimized opt-in, we're happy with it, and now we just want to work on implementation. So opt-in becomes what we call a sealed intervention. We're happy with it, we're not going to mess with it. And the implementation of opt-in becomes a wraparound intervention. The implementation itself is an intervention, and you can use most to optimize this wraparound intervention. You would develop a conceptual model of the implementation process, identify candidate components of the implementation, select an optimization objective, and conduct an ORCT as if you were working with any other evidence-based intervention. And we'll be discussing this. These are some resources at CADIO that you might be interested in. And I will stop my screen share now. Okay.
All right, great. Give me just a second and I'll switch. Okay. So I am going to be, as Linda mentioned, getting into a little bit more detail about the decision making that can go into the optimization process. And I'm going to do this sort of in two pieces, addressing two areas of new research in most that are relevant to implementation science. In this first area, I want to give a shout out to our colleague, Kate Guastafaro, who's also an associate director of CADIO. Kate is an implementation scientist and intervention scientist, and a lot of this content that I'm presenting here draws upon some work that she's been doing. But let's start with a hypothetical example. So suppose we have an intervention scientist who wants to optimize a multi-component intervention to target medication adherence in a population of interest. So they've identified 4 candidate intervention components, and we'll assume that in this case, they're trying to develop a fixed intervention or an intervention that is going to be containing the same components for all participants. They've created a conceptual model of this intervention where each of the candidate components targets a particular hypothesized mediator of change in medication adherence. So we have motivational interviewing sessions, which are intended to target health beliefs, which are intended to improve medication adherence, and so on. So this hypothetical investigator conducts a 2 to the 4 factorial optimization RCT. And so what that means is that there are 2 to the 4 equals 16 different experimental conditions that participants in this hypothetical experiment are randomized to. In this particular design, I'll just emphasize that to estimate the main effect for motivational interviewing, for example, we would be comparing the conditions in which motivational interviewing is set to on to the conditions in which motivational interviewing is set to off. So these experimental conditions, in other words, should not be considered arms. We're not ever comparing individual conditions. We're comparing different strategic combinations of conditions to estimate different main or interaction effects. If I were to toggle between these, you might notice that in the rest of these factors representing the different candidate intervention components, there's balance. So we have 4 conditions in which peer support is on, 4 in which peer support is off, and so on. This is part of what makes the factorial experiment as efficient as Linda was alluding to before. So using these different main and interaction effects that are estimated in their factorial experiment, this hypothetical investigator can get an expected outcome for each of 16 different possible versions of this intervention, where these different versions contain different combinations of the candidate intervention components. In this plot here, I've put these with letters for simplicity, where we can imagine that A is motivational interviewing sessions, B is peer support, and so on. So in this plot, there's the expected outcome. In this case, it would be an expected medication adherence outcome on that x-axis, and the cost to implement the intervention is on the y-axis. So interventions that fall farther to the right of the plot have higher or better expected outcomes, while interventions that fall farther to the top of the plot are more expensive. In this set of simulated results, intervention A, B, C, D, or the one that contains all 4 of the intervention components, is the most effective. It has the largest expected outcome, but it's also the most expensive. It falls farthest to the top. So the solid line highlights alternative intervention versions that can be considered efficient in their use of resources. The circled one, for instance, intervention ABC, is almost as effective as intervention ABCD, but considerably less expensive. So if this investigator's objective is to identify an intervention that is expected to be effective, but also practical to implement, they might think through these trade-offs carefully and decide that intervention ABC is the one that is successful in carrying out that strategic balance, that it's effective enough, but also practical to implement. This is using the methodology that Linda referred to, DAVE, Decision Analysis for Intervention Value Efficiency. If you'd like to read more about this sort of strategic balancing, you can check out this paper we've put out in Health Psychology recently. But to proceed, let's imagine that the intervention scientist has picked intervention ABC, so the intervention that contains motivational interviewing sessions, peer support, and the navigator. As Linda was mentioning before, this intervention, since it's now chosen as the optimized intervention, becomes sealed. So let's suppose next that this investigator wants to consider building a wraparound intervention to support the implementation of this sealed intervention package. So now they identify candidate components again, but this time the candidate components are implementation strategies. The outcome of interest now is an implementation outcome, adoption of the intervention in clinics. And so now in this particular conceptual model, we see that these different candidate implementation strategies are targeting the implementation outcome through hypothesized mediators as before, but this time as mediators of change in that implementation outcome. You also can note that at the far left of this conceptual model, there's a purple bar reminding us that in this case, the sealed intervention is a constant. So everybody is getting that. What we're manipulating here are these candidate implementation strategies. So proceeding much like we did before, they can conduct a factorial experiment varying these candidate implementation strategies. They can estimate main and interaction effects for the different implementation strategies. And then using those main and interaction effects, they can estimate expected outcomes for the different versions of this wraparound intervention containing different combinations of implementation strategies. This plot shows what it might look like if they were to use Dave to pick an optimized wraparound intervention. So again, we have the expected outcome on the x-axis. This time it's an adoption outcome. But interventions that fall farther to the right are still performing better. And interventions that fall higher on the plot are more expensive. So this particular result would highlight two alternatives potentially: interventions CD, which contains supervision and the referral system, and another value efficient alternative, intervention C, which just contains supervision. So again, this hypothetical investigator would consider the relative balance between the expected implementation outcome and the cost of delivering these different wraparound interventions. In this case, they might decide that the effect that CD produces on adoption is worth the cost relative to the alternatives. So if they were to proceed this way and think that CD were worth the cost, then again, we would now have an optimized wraparound intervention. So this picture is supposed to depict the fact that we have an optimized intervention, that's the box, and you remember that contained motivational interviewing, peer support, and the navigator. And now we have optimized a wraparound intervention to support the implementation of this intervention. So why is this something to emphasize? For one, when we're thinking in terms of implementation science and implementation strategies, we might have to remind ourselves the same thing that we have to remind ourselves when we're thinking about intervention content, namely that more is not always better. Sometimes there are little antagonisms that might be due to burden, say. And so it's not always true that the intervention that contains the most will perform best. But importantly, implementation strategies, just like intervention components and of content, also incur costs. And that means that it's worth asking whether a particular strategy contributes to the desired implementation outcomes, whether that's individually or in combination with other implementation strategies, to an extent that justifies its costs. We see that there is great opportunity for the field of implementation science and intervention optimization to come together to innovate in this space. We've been doing a lot of work developing methodology in intervention optimization that would be quite relevant here, including methods for optimizing for multiple outcomes, as Linda mentioned. Those could be multiple implementation outcomes, so maybe it's adoption and reach, for instance. It could mean that we're trying to optimize for implementation outcomes and health outcomes at the same time. It also could mean that we're trying to consider equitability as another criterion in the optimization process, which sort of tees up what we'll be talking about next. To sort of once more emphasize something that Linda mentioned before, there's a lot of progress towards successful implementation that is made simply by optimizing an intervention itself, the evidence-based intervention, so that it's effective and doesn't contain components that might be considered redundant or might not be contributing. And so this sort of optimization of a wraparound where we've sort of seen this investigator go through these various steps, that might not be fully necessary in every case, but it represents certainly a very interesting way that optimization and implementation science can come together. For a little bit more on the integration of intervention optimization and implementation science, I'll refer you to this paper that Kate Guastafaro and Linda put out a little while ago. So this brings us to a switch in topic, but still within this realm of decision-making, identifying optimized interventions, and considering different trade-offs. And so in this piece, I'll pitch some of our newest work in developing methods that enable the consideration of equitability as a criterion in the optimization process. And then I'll explain in just a moment more what I mean by that. First, I'll also acknowledge our collaborator, Dave Van Ness, on this work. He's a health economist at Penn State. So first, I want to mention what you all probably are very aware of, which is that there's a lot of emphasis on equity, health equity, equitability in the implementation science space. There's a lot being written about this. I've chosen here to highlight this particular paper, which contains a quote that I found really impactful, that every project in implementation science should include an equity focus. We should, at a minimum, ensure that we leave no one behind and that existing disparities are not widened. So with this idea in mind, I want to note an important challenge, namely that many of the interventions that we're developing, whether they're behavioral, biobehavioral, or biomedical interventions, are interventions that are intended to be disseminated broadly. So in other words, they're intended to be delivered to participants who vary in their social, environmental, and economic advantage. When interventions are intended to be disseminated so broadly across a population, there are at least two goals. The first is to achieve effectiveness overall, so in terms of the sorts of mean outcomes we've been talking about so far. But a second is to achieve effectiveness equitably. So in terms of a distribution of outcomes, or the question of, are the effects of the intervention being experienced across that distribution of participants, regardless of relative advantage, socially, economically, environmentally? It is possible for this first goal to be met when the second is not. So say because the intervention is really effective for just some people within the population. And in these cases, broad dissemination of that intervention carries an important risk, or namely that existing health disparities will increase. This is a phenomenon that has been coined intervention-generated inequality, or when an intervention that's effective on a population level increases a health disparity. It has unfortunately been documented in various areas of public health, and quite notably in smoking cessation, tobacco cessation interventions specifically. So let's return for a moment to our hypothetical investigator with their candidate intervention components. Again, this investigator was trying to target medication adherence as the outcome of interest. But now let's imagine that the investigator believes that different components of these candidate intervention components are more or less likely to contribute to intervention-generated inequality. So say, for example, that motivational interviewing sessions is delivered in a clinic setting, and therefore this investigator hypothesizes that individuals who are already advantaged, who are already successfully engaged in the healthcare system, will be more readily able to benefit from this component. So suppose now that with that in mind, the investigator chooses to include this navigator component that is supposed to buffer this tendency in motivational interviewing sessions. So maybe the navigator is supposed to make the benefits of motivational interviewing more fairly experienced. So now this investigator has hypotheses that line up with this topic of equitability. And we remember what we've already noted, that there are 16 different possible versions of the intervention package. Here are a few of them. And you remember that one of those versions included all 4 of the candidate components. It could be that this intervention containing all 4 of the candidate components would achieve the sort of balance that the investigator is concerned about. Maybe that tendency in motivational interviewing sessions to concentrate its benefits among those who are more advantaged is successfully buffered by the navigator, and so forth. However, we already saw that this intervention version with all 4 components is also the most expensive. And so maybe if this is the intervention that is to be disseminated broadly, maybe in practice, components of this intervention are likely to be cut ad hoc because it's simply too expensive to implement in full. If that's the case, then maybe that sort of careful balance the investigator has set up is threatened. So there are different versions. Maybe the version that contains motivational interviewing sessions and peer support has a really strong impact in terms of that overall population effect, but maybe that effect is more concentrated among those with more advantage, threatening an impact on intervention-generated inequality, and so forth. Now that the investigator has these considerations, this means that the different versions of the intervention may vary in their performance, specifically in terms of equitability. So we already saw this result where the investigator estimated an expected outcome in terms of medication adherence for each of the different intervention versions. But with this sort of result, the investigator is focusing on mean outcomes, and the results express that sort of overall population effect. This sort of decision-making does not incorporate the effects in terms of the distribution that the investigator is interested in. So we can also use a health concentration index to get at the question of how much tendency these different intervention versions show to concentrate their benefits among different portions of the population. So this result emphasizes, for instance, that the interventions that fall farther to the right show more tendency to be beneficial specifically for individuals who are already advantaged, whereas the individuals or the interventions rather that fall farther to the left do not show that tendency. We have summarized this in terms of disparity reducing potential on the one hand, disparity increasing potential on the other, but this is a complicated concept we could return to discuss. But in any case, the investigator has now kind of gotten at this additional dimension to performance that they care about. this question of how the effects of these different intervention versions are distributed. So what the investigator wants to do now is to bring everything together. And so they can do this by taking the information that was presented in the previous plot with a balance between the expected outcomes on a population level and cost, combining that into the concept of net health value that gets at that mean outcome and the efficiency of resource use, and also then balancing with equitability. So this particular solid line highlights alternatives that might be considered with all of these different criteria in mind. So just to play out this scenario for the investigator, I know we want to get to questions in a moment, so I'll just go through this rather quickly. We have interventions A, B, and A, B, C that are quite positive in their net health value, but on the negative side of this equitability concept, and intervention BC, which stands out as one that is more positive in terms of equitability. You might remember ABC. This was the one that this hypothetical investigator selected in the balance and even considered a sealed intervention for eventual implementation. But these results would suggest that while ABC might be a useful intervention on a population level, it may show a little bit of tendency, if it's disseminated so broadly, to perform in the concerning direction in terms of equitability, maybe with some potential to contribute in an undesirable way to intervention-generated inequality. One of the ways that the field of implementation science sometimes addresses the goal of equity is to emphasize reach and taking an intervention and increasing the reach of the intervention. But one of the key points here is that if we're not also considering the equitability of the effects of that intervention, if we increase the reach of an intervention, if we disseminate it that much more broadly, we may actually be adding to the effect in terms of intervention-generated inequality. Just a very brief concluding note that as we've touched on, most is being applied to optimize multi-component interventions across various areas of public health. This methodology for this sort of strategic balancing that we've been talking about is in very active development. This work in equitability in particular is quite new. We just wrote about this in prevention science. And there's a lot still to be done to keep working out these methods. Briefly, I'll say we have resources at CADIO's website, as Linda mentioned. We also can refer you to our sister center, the D3 Center at the University of Michigan, that particularly focuses on the optimization of adaptive interventions and puts a lot of effort into disseminating information about SMARTs. We also have trainings on most that we deliver regularly that make use of a Coursera course about most that is available for free. We recently added a second course that is aimed at methodologists and biostatisticians. And I would encourage you to sign up for our newsletter and our webinars and to generally be in touch with us. And my chat bubble suggests there might be questions, so I'll open it up for discussion.
Great, thank you so much. Some of the chat was related to some technical difficulties. Some of us are still learning how to use the Zoom workplace and finding the slides. But we do have, I'm glad you actually brought up that issue about training specifically for biostatisticians. One of our biostatisticians actually had a comment. Joe, did you want to unmute?
Sure, and I apologize for any background noise. My kids are off school today. So I found that this was a fantastic presentation. And it looks like you're using some of the similar techniques that are used in like quality improvement studies where you have inputs and outputs. And so you're kind of comparing different units based on the balance of resources utilized versus results that are produced. So I was wondering if you had any input or any insight into, like, when you're comparing that balance between two of those points on that graph, how are you accounting for the uncertainty in that comparison?
That's a great question. That is something that we are continuing to grapple with a little bit. And so I want to say a few things. First of all, we can readily estimate uncertainty. The results that I was presenting here are produced using Bayesian analyses, so the uncertainty could be expressed in a Bayesian way. The ability to estimate uncertainty is not specific to the Bayesian paradigm, of course, but in this case, we could even generate probabilistic sorts of comparisons among those dots. And I think that those could be very useful. But another thing that complicates this a little bit is that we tend to make a contrast between what Linda has called a decision priority perspective and a conclusion priority perspective. And in a lot of science, we're accustomed to thinking in a conclusion priority sense, where we're trying to make a strong scientific conclusion about a particular effect that might stand up in science court, so to speak. Whereas in the optimization phase of most, what we're really trying to do is we're trying to make the best possible use of the available evidence to inform a decision about what to move forward with, acknowledging that moving forward with nothing is also a decision. And so that means that the best way to use this uncertainty information might be a touch different. And so this is something we're continuing to think about, but certainly a very good question.
Thank you so much, Dr. Beffert. We're going to get to you, but I think we've got to take care of Dr. Castro's disbelief. Dr. Collins or Dr. Strayhorn, did you see that in the chat? This is magic.
Yes, I'm amazed that factorial
that
experiments can test for interactions with a reduced sample size. Can you educate the non-statistician about how this works? Well, I'm not, yes, I can, but it might be hard in this context, but I will tell you that when it's a 2 to the k factorial experiment, that is, each factor has 2 and only 2 levels in the factor, and you analyze the data using regression, which is what we would ordinarily do, you have the same power for a regression coefficient of a given size, no matter whether it corresponds to a main effect or an interaction of any order. And if you don't believe me, that's in Cohen's book on power.
And I think that's why Dr. Strayhorn, I think, was showing us the importance of the balance across the groups on the other aspects, regardless of their intervention.
Balance is important, although that what I just said holds approximately, unless balance is really off.
Okay. And I'm glad Dr. Wick's here, because Dr. Castro, we will have to rely on some of our biostatisticians to help us with this. I think this is going to be fun to talk about more. Dr. Beffert.
Yes, thank you. That was awesome and got me thinking about a lot of stuff. And thank you, Ed, for inviting Linda and Jillian to present for us. So I have seen most commonly used for mHealth digital interventions, and which I see its applicability in that space, particularly in optimizing for resources. A lot of your examples were using components that are based on human interaction and human factors. I love the part about considering human factors on the recipients and how that may drive further disparities. But I get a little hung up on what's inside that box when you want to seal that intervention as something that's effective, when there's highly variable human interaction that's happening that many times it's not about whether it's MI plus peer support plus navigation, it's more about the skills and the expertise and even the style of the humans that are delivering those components. And that sometimes I think can be overly minimized or overly simplified by saying, well, we're going to do fidelity monitoring. I mean, you can do fidelity monitoring and complete a checklist, but it doesn't necessarily mean you've really optimized, you know, the training and the level of skill, and then maybe even the selection of the individuals delivering that component. So I just kind of throw that out there. I mean, I do more traditional trials, and I'm used to thinking of varying degrees of control on those kinds of things, dependent on when it, you know, if it's either effectiveness where you're using your own people that you can control the training versus pragmatic where you are, you know, using a training strategy that's real world and you're allowing that variability to take place within the design itself. But how do you guys see that the role of those components in most when the components involve that human interaction?
Yeah, so can I just, I want to give Jillian a chance to answer this too, but can I just ask Christine, there's probably something I'm missing here. How is this different in most than it would be in the classical approach? How is this more of an issue in most than it would be in the classical approach?
I mean, I'm thinking of where I'm thinking of trials where we're testing a package. So we're not necessarily trying to optimize it for efficiency, but instead we're testing a package under certain conditions that we have specified and, you know, built into the design with, you know, whether it's effectiveness or pragmatic, we have different levels of control over these things, but it's kind of built into the design and we're accepting that as is, and then, you know, sort of testing outcome from that package deal. So it's
and then you're saying you would not expect the results to generalize outside of those boundaries?
Well, I think you sort of think of it as an average. You kind of go into it thinking you're going to have an average with a range of skills or style or whatever it might be for that package deal, but it's large enough that, you know, that average could replicate.
Okay, so I'm sorry, I'm still not seeing the particular challenge to intervention optimization here.
Well, I guess I'm thinking
as opposed to the classical
the
approach.
particular combination that you've selected based on that particular trial may not replicate, depending on some of the implementation strategies for that approach, like the training strategy, or you know what, like that the implementation part is actually built into the component itself. Maybe I'm getting too complicated. I'm having a hard time even.
No, I don't think you're getting overly complicated. So I think what I'm about to say, I think applies to a classical RCT or an optimization RCT. You can either set up your design so you can model that stuff or not. And most people don't set their designs up that way, but you can. And interestingly, we just had a visitor from the UK, Rebecca Walwyn, who is working on optimization trials really elegant optimization trial designs that would enable modeling of some of what you're talking about. So I do think that's an important issue. But Jillian, do you want to comment on this?
Yeah, I was just thinking some about the opt-in example you gave at the beginning, Linda, and it might be useful to just think a little bit more detail about that example. So for instance, in that example, I'm thinking in particular of two components. The first one was coaching calls. And in that component, there were trained coaches.
Yes.
And there was very careful fidelity monitoring.
Yes, very careful.
It was sort of done in your kind of way that you would do if that was going to be included in a package as well, but it involved a lot of oversight. But an interesting contrast is with another component, which was buddy training. And so buddy training was defined. So I think Linda mentioned everybody who came into the study needed to identify a weight loss buddy. The component was training for the buddy. but there
Mhm.
was sort of no promise about what the buddy was doing and how well they were doing it. It was just
Right.
provision of training or not providing
Mhm.
any training.
But the training was very carefully done by trained trainers. But yes, everything you're saying is correct.
Right. And so any conclusions that are drawn about buddy training aren't necessarily conclusions about the buddies, but about the provision of training versus not. Whereas the conclusions about the coaching are more about this coaching process as defined by the study team. I don't know if that's useful in thinking this through, but I think everybody, when they're dealing with components that involve humans in a bigger way, there is this question of granularity and how you're defining the component and whether training is separate, is that an additional component? And I think that's one of the reasons the process of arriving at a conceptual model for the intervention and also an objective driving everything of what are we really trying to optimize is really important.
Yeah, I think that's a really great example, and it is kind of what that example was what triggered this question for me, partially because I do obesity research too. But I think when we start mapping out, these are the components in this combination that are this amount of efficiency for this outcome, we have to define those components in their entirety, which includes how they were implemented.
Yeah, definitely.
So we're at the top of the hour. Thanks everybody for joining us. I did want to say that this session was co-sponsored by our new COBRI on implementation science and equity. And we are actually having a post-presentation discussion. So if you had some additional questions that didn't get answered, you're welcome to stay on with us. We're going to stay on this